Hello and welcome to another lecture of classical motion of a single particle. We already have discussed different interesting properties of Lagrangian and Euler-Lagrange equation, okay, that is the Lagrange's equation of second kind. So, today we will actually discuss something very relevant for our course. So, if you remember that we have already discussed in the framework of single particle motion, we have discussed the Lagrangian of a free particle, we have discussed the Lagrangian of a pendulum, simple pendulum. We have also discussed the Lagrangian of a particle under some central potential, where the potential is a function of r only. Okay. But another thing which we have already discussed, a considerable amount of time was spent for that, that was the harmonic oscillators. Okay. So, today we will discuss the Lagrangians of different harmonic oscillations and also different type of oscillatory systems, okay, and how from some Lagrangian we can get back or recover the well known equations of dynamics of simple harmonic oscillator, damped harmonic oscillator, forced harmonic oscillator, like this. Okay. So, let us start. So, before starting the usual recapitulation I am doing. So, if you remember, we derived the Euler-Lagrange equation is given by d dt of del L del q I dot minus del L del q I is equal to 0 for all I running from 1 to n, where n is the number of generalized coordinates and q I and q I dot, they are simply generalized coordinates and generalized velocities. Okay. Then we said that Lagrangian in general can be a function of qi dot and t. We discussed in the previous lectures many interesting properties of this equation, but the three most important properties were the cyclic coordinates and the conservation of conjugate momentum, that means if a certain qi, okay, let us say qi star is not explicitly present in the expression of Lagrangian, then this is called a cyclic coordinate. If the system has more than 1 degrees of freedom, it is possible to have more than one cyclic coordinates. Okay. So, then if there is a cyclic coordinates qi star, then pi star, which is nothing but del L del qi star dot, is a constant of motion. We also said that if the Lagrangian is not explicitly containing the time, okay, then L minus summation over del L del qi dot summation over I running from 1 to n again is a constant of motion. For ordinary mechanical systems, we showed that this is nothing but minus h is equal to minus the total mechanical energy. So, actually it says that the total mechanical energy is nothing but summation over del L del qi dot minus L, okay, for usual mechanical systems. Systems means consisting on one particle here for our course, okay, systems associated with a V, which is a function of just the generalized coordinates for the sake of simplicity. Okay. Then we said that if my Lagrangian is mapped to another Lagrangian, that is L prime, and which is the old Lagrangian plus ddt of a function f, which is a function of the generalized coordinates and time, then if this is the Lagrangian, valid Lagrangian for a given system, L prime will also be a valid Lagrangian of that set system. Okay. So, L prime, so if is this can be written, then L prime and L are equivalent Lagrangians. That means they produce the same equations of motion. Then also we finally discussed the how to define the Lagrangian of a combined system consisting of two or more than two non-interacting subsystems. Okay. There we just saw that you can just write the combined or resulting Lagrangian as a direct sum of the individual Lagrangians, and the resulting set of generalized coordinates are composed of by the collection of all the generalized coordinates. Okay. So, I will now in this lecture we will talk explicitly on the oscillators. So, for oscillators actually the point is, so here you see the reasoning is a little bit, I mean, so in general we use Lagrangian, we use the knowledge of Lagrangian to find the equations of motion, but now we are actually, since we have learnt a new technique, what we will do, we will first take some systems for which we somehow know by other means, actually like by traditional method of Newton, force balance method, or D'Alembert's principle, or Lagrange's equation of first kind. Okay. Whatever you use, let us say you have already known their equations of dynamics. Now, what we will do? We will do the other way around, the play is now in the backward direction. Okay. That means, we starting from those equations we try to intuit what are the Lagrangians. Okay. And then finally, from those Lagrangians finally we use that Lagrangian, we pose that Lagrangian, and then what we will do? We will simply cross check whether the equation of motion which is finally obtained by solving the Euler-Lagrange equation, okay, is the same equation as that of the known system or not. Okay. At this point I would like to emphasize on one point, that when we solve the Euler-Lagrange equation, okay, basically by solving the Euler-Lagrange equation we do not solve the motion of the system. The solution of an Euler-Lagrange equation itself is an equation of dynamics, okay, or some information about the motion of the system, but it cannot be taken as directly the solution of the motion. That means, q as a function of t, q dot as a function of t, like this. Okay. So, this is not the end of the story. So, solving Euler-Lagrange equation simply gives us the equations of motion, but finally once you have your equations of motion or the equations of dynamics, then you have to further integrate by using the methods which I discussed in the very first 2 weeks. Okay. You can finally have the solutions depending on whether you can integrate them successfully or not. So, for 1D simple harmonic oscillator, so here you see that I am just in advance I know that this is the case for simple harmonic oscillator. In general, if the proper target of Lagrangian has to be fulfilled, then what should be done? That I do not know that how it should look like, because whenever you say this is a simple harmonic oscillator, you are assuming that you know that the particle is moving and performing a simple harmonic oscillation. Okay. But in general, if Lagrangian is known, that does not say that you know the motion, because once you know the Lagrangian, then your next duty is to solve the Euler-Lagrange equation to find the equation of motion. And then when you find the equation of motion, you again solve this for the motion, So, q as a function of t, q dot as a function of t, and finally, you can come with your conclusion that okay, maybe this is now corresponding to a simple harmonic oscillator or a damped harmonic oscillator. Okay. But here we start from the statement that okay, we try to construct Lagrangian for the 1D simple harmonic oscillator. So, the prescription, so what will be the Lagrangian? L. Okay. So, since we know such a system is having, so when I am saying system, it is a particle, such a particle okay, is having kinetic energy. So, it is in 1D. So, kinetic energy is equal to half m x dot square, and so I can call that T, and potential energy which is V is equal to half k x square. Okay. Then following the recipe L is equal to T minus V, we can write L is equal to T minus V. So, that is half m x dot square minus half k x square. Okay. Now, what will be the Euler-Lagrange equation for such system? That will be simply the Euler-Lagrange equation will be d dt of del L del x dot minus del L del x will be equal to 0. Okay. And then del L del x dot is nothing but m x dot. So, you will have d dt of m x dot, and this is nothing but minus of, so del L del x is k x. So, minus of minus k x del L del x. So, it will be minus of minus k x is equal to 0. So, you will have m x double dot plus k x is equal to 0, and k by m you can define as omega 0 square if you want, which is a constant, and you can say okay, if my k is positive, m is positive, then it is also positive, and for that case I can actually write this equation, which I know is the equation of a simple harmonic oscillator. Okay. But now, in the next step I will not follow the same way. I will give you Lagrangian, and then we solve the Euler-Lagrange equation, and we together understand exactly to which system this Lagrangian is corresponding. Okay. So, let us take the Lagrangian L is equal to half m x dot square minus half k x square times e to the beta t, where beta is a constant. Now, you will say what type of Lagrangian is this? Starting from the beginning, starting from the derivation of Euler-Lagrange equations, we showed that Euler-Lagrange equation is actually satisfied for Lagrangian of the form t minus v. But then of course, I claimed that Euler-Lagrange equation is true for Lagrangians which are even not in the form of t minus v. Okay. So, in this example we will see such an example, and you will see that how it is relevant to our discussion. So, if you have a Lagrangian like this, where beta is a constant, m is a constant, and k is a constant. So, this Lagrangian also explicitly depending on t. Okay. So, the first point is that in this Lagrangian, if I now try to solve the Euler-Lagrange equation, what will be del L del x dot, that you have to calculate now with caution, because there will be e to the beta t times it will have m times x dot. Okay. And del L del x, that will also be e to the beta t times minus kx. Okay. What is now the ddt of, so ddt of del L del x dot? Do you know how to do that? If you do that properly, you have to write this e to the beta t m times x dot. So, it should have two terms, one will be m e to the beta t x double dot plus m x dot, then ddt of this term will be with beta e to the beta t. Okay. So, yes, that is the term we get, the beta, yes. Okay. Yes, I think this is correct. And finally, Euler-Lagrange equation gives this m e to the beta t x double dot plus m beta e to the beta t x dot minus of minus k x times e to the beta t is equal to 0. And you have, since e to the beta t is not in general 0, okay, we can write m x double dot plus m beta x dot plus k x is equal to 0. Okay. So, if you now write this, you will actually see that I can just divide the whole thing, whole equation by m, and I can write beta x dot plus k by m is equal to a 0. Now, I call beta as 2 lambda and I call this as omega 0 square. What would you get? You get the famous equation of a damped harmonic oscillator. Okay. Now, you see that although this Lagrangian was looking strange, actually this Lagrangian is a valid Lagrangian. Why this is a valid Lagrangian? Because when it is put in the Euler-Lagrange equation, it is actually giving us a meaningful equation which we already know from our knowledge. Okay. But now, the point is why it is not in the form of t minus v. That is also easy to understand at this point, because t minus v is a representing a Lagrangian for a system which is associated with a potential, okay, only. That means that there is the kinetic energy and the potential energy, okay. And that means that the particle is actually, from your knowledge you know, is in a conservative field, and its total mechanical energy, which is a function which is t plus v, is conserved, because del L del t was equal to 0. Here the first thing is that your del L del t is no longer equal to 0, okay. And that is the first indication you have that maybe this system is not the system where t plus v is conserved, okay. And this is quite understandable, because you know that for a damped harmonic oscillation or damped harmonic oscillator, the total mechanical energy is not conserved, because this is not a conservative system. Okay. I am going to another example where you will again have a little bit of strange feeling. So, I use again the blue color. So, we now take the Lagrangian, okay. L is equal to half m x dot square minus half k x square plus x f, which is a function of t only. Okay. I do not know what f is, but this x is just the coordinate. I am talking of one dimensional motion. Okay. This is actually looking like very much the harmonic oscillator Lagrangian plus something. Now, first question is, you just have a look first that this equation is not explicitly independent of L. Okay. It has t, because this f is an explicit function of t. So, del L del t is not 0. Okay. Again, in this equation you do not have any cyclic coordinate. Okay. So, no conservation for any conjugate momentum. Then I actually have another observation, that is, this is something added to the old Lagrangian of a simple harmonic oscillator. So, is if t times x can be written as ddt of a function g, which is a function of x and t? I think no, because if your equation has an x associated with this like this, then this cannot be written like this, because even if there is an x in this g, when it will be operated by ddt, it will give you at least one x dot. Okay. So, this type of thing actually can tell you already an indication, can give you an indication that this is not the case of an equivalent Lagrangian. Okay. Then what to do? We will simply be obedient enough to solve the Euler-Lagrange equation for L. So, del L del x dot will be what? So, it will be m x dot. Okay. There is nowhere, I mean, other than this place there is no x dot, you can see, okay, in this L. Then what will be d dt of del L del x dot? That will be simply m x double dot. Now, what will be your del L del x? That is a little bit tricky, because from this term you will have minus k x, but on the other hand, from this term you will have plus f t. Okay. I write, so Euler-Lagrange equation again gives m x double dot minus kx plus f t and is equal to 0, and that is m x double dot plus kx is equal to f t. I can again divide the whole thing by m, I can have this, and let me ask you whether you can recognize this equation. So, this equation is nothing but the equation of a forced harmonic oscillator without any damping. Again you see, this is a Lagrangian which is not exactly in the t minus v form, and also you see del L del t is not equal to 0. So, that means that you have to think that this Lagrangian is not corresponding to a conservative system, and that you know by knowledge, because if an oscillator is just getting forced from outside, but it has no sink of energy by some dissipative term, then its energy is actually growing in time. So, energy is not conserved. Okay. So, you see that again a Lagrangian which is not in the form of t minus v can give you forced harmonic oscillator. Exercise for you: what will be the Lagrangian for a system or an oscillator with both forcing and damping, so that the final equation of dynamics becomes x double dot plus 2 lambda x dot plus omega 0 square x is equal to some f of t by m. Can you do that? Okay. I am going to another very interesting point considering the Lagrangian of the oscillator. Okay. Let me now take a Lagrangian which is half m, always 1D oscillator, half m x dot square minus half k x square. Now, I will have something extra plus beta times x dot. Okay. So, I can actually now think, well, I can think this has a form which is still t minus v, but this is t and this part. So, I can now write this part is actually v prime, which is half k x square minus beta x dot, but this v is not a function of coordinates only, this v is a function of velocity as well, okay, because it contains x dot. Okay. Then the first conclusion you can draw, okay, so that means that maybe it is not related to a conservative system. Okay. So, maybe it is again representing an oscillator with some damping or with some extra effect where energy is maybe not conserved. But another point at the same time I am trying to tell you that also check whether the Lagrangian is explicitly containing t or not. Then you can say, oh, that is true, this Lagrangian is again explicitly independent of t. So, del L del t is 0. So, something is conserved. Now, is that something be a meaningful quantity for you like mechanical energy or minus of mechanical energy, or we do not know. Again the solution is solve the Euler-Lagrange equation. You see, whenever you have a problem, confusion, doubt, okay, you split into, okay, you solve the Euler-Lagrange equation instead of concluding immediately, we solve it. Now, what will be del L del x dot? Now, it will be m x dot, okay, plus beta, because there is a term associating x dot which is linear in x dot. Okay. Now, what will be then ddt of del L del x dot? That will be m x double dot, and what will be del L del x? That will be minus k x. So, Euler-Lagrange equation gives m x double dot minus k x is equal to 0. That means x double dot plus omega 0 square x equal to 0, which is again exactly the same of a simple harmonic oscillator. This is quite strange, because now you see that your V, I mean the potential part is explicitly containing the generalized velocity, and we said that in the derivation of Euler-Lagrange equation, we said that t minus v was, the derivation was possible because v was assumed to be a function of generalized coordinates only. So, what is the problem? The point is that no one actually said, so here is the logic, that although if your v, if your Lagrangian has a t minus v form, okay, and your v is explicitly is a function of coordinates only, generalized coordinates only, then you can derive the Euler-Lagrange equation. That means your Lagrangian can satisfy Euler-Lagrange equation, but there is no prohibition or there is no restriction that if you have a form t minus v where v is a function of generalized coordinates and generalized velocities, cannot satisfy Euler-Lagrange equation. Now, finally, the point is, I understand everything, but is there any other point by which I can even understand a little bit better? That means using some concept which I have already learnt in previous lectures. Just remember the very last property which I discussed as a recapitulation today, this one, okay, the concept of equivalent Lagrangians. You have to be sure on one point that if two different Lagrangians produce the same equations of dynamics, they are equivalent Lagrangians. So, either one is just the other plus some constant, or the one is the other plus minus some ddt of some function which is a function of x and t only. Here what is the mystery then? Here when you are writing this Lagrangian, this Lagrangian is nothing but Lagrangian of simple harmonic oscillation, which is just this part, okay, plus this. Now, beta is a constant, and what is x dot? This is ddt of x, and that we forgot. So, x dot is nothing but ddt of x. So, what is this? This is ddt of beta x, which is a function of course x and t. I mean here this is just a function of x. So, we have no problem. So, this is a Lagrangian which is an equivalent Lagrangian of the Lagrangian of a simple harmonic oscillator, and that is why although it looks a little bit strange for you maybe for the first time, it will give you always the equations of dynamics of a simple harmonic oscillator. Finally, before wrapping this lecture up, I will give you another important but interesting example. That is, I have a Lagrangian now half m x dot square minus half k x square plus let us say alpha t cube by 3. Now, you see what will be your observation? Again this is the Lagrangian, I now have a good name for this, LSHO, yeah. So, this is Lagrangian of the simple harmonic oscillator plus something, again the same business, and that plus something what will it do, that we do not know. Okay. Now, you see the first conclusion is there is no cyclic coordinate, only one dimension x and x dot both are present. So, no cyclic coordinate, no conservation of conjugate momentum. Is the Lagrangian explicitly depending on time or not? The answer is yes. So, del L del t is actually not equal to 0. Okay. So, you can see that already there is an indication that some non-conservative system can be represented. Okay. However, if you are smart enough, you will say, well, look, give me 1 second, I will re-look at this part. What is this? This is a function of t only. Okay. I can say, okay, do I know G such that dg dt is equal to alpha t cube by 3? I can then say, okay, let us do something like that, G should be equal to alpha t cube dt by 3, and if you integrate, actually just doing some, I mean proper integration constants, okay, you can get rid of the arbitrary constant and you can actually say, okay, this G is nothing but alpha, I mean t to the power 4, so it will be 12. Okay. So, actually if I say that G is alpha t to the 4 by 12, then dg dt will simply be alpha t cube by 3. So, again here you see this Lagrangian is SHO plus a function of t, and not only that, this is also a function ddt of a function of t here, where G is this. Then you say, well, this is the equivalent Lagrangian. So, on one case we saw that the Lagrangian is equivalent to the Lagrangian of a simple harmonic oscillator. On the other hand, we saw that del L del T is not equal to 0. So, the function which we defined, so if you remember, if this is not equal to 0, then of course L minus summation over del L del Q I dot Q y dot is not conserved. But we have seen for a simple harmonic oscillator, this is equal to the total mechanical energy. You can check, okay. I can if you are not convinced, I can show you immediately. So, just for LSHO, half m x dot square minus half k x square, and that is why you can always have, so this function is, so LSHO minus del LSHO del x dot is nothing but half m x dot square minus half k x square. This will be nothing but minus m x dot square, which will be minus half of m x dot square plus half k x square. This is the total mechanical energy for a simple harmonic oscillator which is conserved. We know, we directly can show this conservation also from the equations of motion. Okay. Are you getting confused? So, physics is of course always self consistent. There is no reason for being confused if you understand the thing. The thing is, first conclusion is this Lagrangian is certainly an equivalent Lagrangian of LSHO, and that is why that if you solve the Euler-Lagrange equation, let us solve that also. So, I have L, so let us solve the Euler-Lagrange equation. Okay, for L, which gives ddt of del L del x dot minus del L del x equal to 0, and L is equal to half m x dot square minus half k x square plus alpha t cube by 3. Okay. For this, for Lagrangian this, we have del L del x dot will be simply equal to m x dot, and so del L del x dot under d dt will simply always give you what? M x double dot, and then del L del x is again minus k x. So, Euler-Lagrange equation will give you m x double dot plus k x is equal to 0, okay, or x double dot plus omega 0 square x is equal to 0. Simple harmonic oscillation. So, we are convinced that the conclusion about the equivalent Lagrangian was 100% correct. Now, what about the conclusion of this non-conservation and this del L del T not equal to 0, but on the other hand we know that the total mechanical energy of a simple harmonic oscillator is conserved. Okay. This is also easy to solve. We have to understand that for this system, of course, half m x dot square plus half k x square is conserved. But let us now calculate this quantity for this Lagrangian, this quantity L minus del L del x dot x dot. If I calculate this, I will have, so L is half m x dot square minus half k x square plus alpha t cube by 3 and minus del L del x dot is this one. So, with multiplied with getting multiplied with x dot, we will have this, and that is why finally you have minus half m x dot square plus, I mean within minus actually, half k x square plus alpha t cube by 3. Now, you see that this expression is now no longer equal to minus of t plus v, but it is now minus of t plus v plus something else. And you see that is the solution of the confusion, that is the Lagrangian actually gives a system which is a simple harmonic oscillator. Now, that system has a conservation, that is this conservation, okay. But this quantity is no longer equal to this quantity for that Lagrangian. So, this quantity is now something which is not conserved because of this term, and that is why we are also reconciling the fact that if we have a Lagrangian for which del L del T is not equal to 0, okay, this is not conserved. Okay. So, you see whenever we give you a Lagrangian, there are always different ways of concluding about this, but you also see that if the Lagrangian is not a very usual one, the most of the time it is possible to get confused. So, the first point is that whenever you see a Lagrangian, you first check that whether the Lagrangian is a valid Lagrangian, okay, and for that what you have to do, you have to solve the Euler-Lagrange equation and just to check that whether this Lagrangian is giving you the equation of some well known system, okay, or some meaningful system even if it is not well known. Okay. Second thing also, if you, and actually for some competitive exams these things are actually should be done first with some caution, that you check for the cyclic coordinates, and if cyclic coordinate is present, then you know some quantity is conserved already, for example conjugate momentum. If L is not explicitly containing the time, you have another conserved quantity, that is L minus summation over del L del Qi dot. Okay. But this does not say that, and finally of course, if you can observe that your L is some well known L, familiar L plus minus ddt of a function of x and t, I mean for 1D of course, for more than 1D you can have x y t or x y z t whatever, yeah, okay. So, then you know that those two will actually produce the same equations of motion. So, the summary of all these things is that if you are somehow successfully identifying different conserved quantities or different interesting properties of a Lagrangian with 100% certainty, do that before solving the Euler-Lagrange equation. But whenever you are thinking that there is a problem, and even if you do not face a problem, for example, I myself, whenever I see the Lagrangian, even without thinking anything, I first solve the Euler-Lagrange equation. So, there is no substitute for solving the Euler-Lagrange equation to first get the equations of dynamics, and after that of course you can think and you can search for different type of symmetry. The final point is just concerning the last examples. You see that the last Lagrangian, which is actually this Lagrangian, okay, a priori it does not give us any information about a conserved quantity which is actually this one, okay, for this system. So, if you do not find any conserved quantity from just seeing that the structure of Lagrangian or the symmetry of Lagrangian, it does not say that the system does not have any constants of motion. Okay. Once again, you have to first solve the Euler-Lagrange equation, get the equations of dynamics, and for that again you search whether there is any constants of motion or not. Okay. Thank you very much.